I'm Donovan Ford. I would like to thank you for purchasing WeldPro's basic TIG welding instructional video. I've been a certified aerospace welder for 10 years. I hold numerous certifications in everything from aluminum to titanium in various welding positions. In this video, we are going to show you how to TIG weld, gas tungsten arc welding, or heliarc. There's a lot of different names for it. We're going to show you how to TIG weld. In this video also, we're going to discuss shielding gases. We're going to talk about argon and helium, CO2. We're going to show you what process you use what shielding gas for. We're going to talk about polarity, AC and DC. We're going to show you how to weld aluminum, and we're going to show you how to weld stainless steel. We're going to show you what a proper weld looks like. We're going to show you how to weld a butt joint. This is an aluminum butt joint. This is a full penetration weld. This is the front side of the plate. That's the back side of the plate. That's what a weld looks like. I'm going to show you what a proper butt joint looks like in aluminum. I'm going to show you what a proper T-joint looks like in aluminum. Show you how to prep your material. That's what a T-joint looks like in aluminum. That's what we're shooting for. I'm going to show you how to weld stainless steel. This is a T-joint in stainless steel. We're also going to show you which polarity to use in which material. There is a common misconception that you can only weld aluminum on AC. I'm here to tell you that is wrong. In the aerospace industry, we commonly weld aluminum DC. We are looking for a driving force in the material. We're looking for penetration. That's what we're looking for. We're also going to discuss torch components. How to assemble your TIG torch, how to assemble and disassemble. We're going to show you the proper parts selection for your TIG torch for the material that you are welding. We're going to talk about gas lenses. This is a standard gas lens. We're going to talk about a standard gas diffuser. This is a standard gas diffuser. Both of those do similar things. They bring gas out of the torch and provide a shielding gas for your arc. Which one is better? That's what we're going to talk about. I'm going to show you why a gas lens puts down a cleaner weld than a standard collet body. We're going to talk about cups, which cups you use for which kind of welding, what you're trying to achieve. Insulators, you want to keep yourself from getting shocked. Tungsten preparation, that is going to be a big one. Tungsten preparation, we're going to talk about what size tungsten to use for what material that you're going to be welding. This is a piece of 3/32, 2% thoriated tungsten. There's all kinds of different tungsten. There is 2% thoriated, there's 2% serrated, there's rare earth. What it amounts to is tungsten and serrated, tungsten being serrated or thoriated is the amount of radiation that each one of them puts off. Thoriated puts off a little bit less radiation. We're going to talk about tungsten preparation, how to prepare that tungsten so that you don't leave a piece of tungsten in your weld puddle. You want to have a clean weld. We're also going to talk about machine setup, how to weld stainless steel, what polarity to use. We're going to be welding stainless steel in a T-joint and a butt joint formation, welding DC. We're going to be welding about a 90 thousandths thick piece of stainless steel, and we're going to be using anywhere from 90 to 130 amps. The same topics will be discussed when we start welding aluminum. I'm going to show you how to set your machine, prep your material, and produce an X-ray quality weld that's going to get you certified, and that's what we're talking about. So let's get started and talk shielding gases in more depth. These are the shielding gases. There's a various number of shielding gases that you use for TIG welding. Because we're going to be welding stainless steel today and aluminum today, the ones we're going to talk about are argon gas, argon compressed gas. That's what you use for stainless steel. You use it for aluminum. You use it for mild steel. That is the most widely used shielding gas that you're going to be using in TIG welding. Right next to it, we have helium. Now, helium is something that is used not primarily in aluminum. The purpose of helium is because when you need a driving force in your material, when you need more heat, when you need it will give you a cleaner weld, a deeper weld when you're using a percentage of it in aluminum welding AC or DC. Typically, I run a 75-25 mix, heavy on the argon, 25 on the helium. Now, that also depends on metal thickness. The thickness of the aluminum, if you're dealing with something a half-inch thick, 1 inch thick, 2 inches thick, then you want to be increasing the helium to 50%, 75%. You can even run helium as a straight shielding gas. The only thing is, when you're running helium straight, a lot of times it has a tendency to oxidize the tungsten very quickly. So you may need to start the tungsten or keep your tungsten clean, because we are talking about X-ray quality welding. Now, everybody's not going to do an X-ray quality weld, but if that's what you're after, then you need to have that tungsten clean. Most welds fail X-ray because of tungsten inclusion. Remember that. Keep your tungsten out of the puddle. There's also another shielding gas that we use in the welding industry, and that is an argon carbon dioxide mix. Now, typically, the argon carbon dioxide mix is something that you use in MIG welding. Now, we're going to cover that in our next instructional video when we discuss MIG welding. But back to TIG welding, we're going to be doing stainless steel and aluminum today. So let's get right to it. I'm not going to bore you with a bunch of bookwork and stuff like that. You want to learn how to weld, and I'm going to show you. Also, when you're mixing your shielding gases for welding aluminum or stainless steel, remember that you absolutely must have anti-backflow valves. You can get these at your local welding supply. They'll have an arrow on them which gives you directional flow, and the purpose of that is so you don't have these are very high pressure gases that go in, you're talking 2,500 pounds of gas pressure, and that's a lot of pressure, and they'll want to feed into each bottle. The lower pressure bottle, the bottles will want to equalize. And if you have a bottle of helium, you don't want your helium in your argon bottle. And if you have argon, you don't want your argon in your helium bottle. You don't want either one to get contaminated. So you run two lines into a Y. But before the Y, you always use your anti-backflow valves and then run it into your machine. Okay, we're back. This is your standard air-cooled TIG welding torch. This is a black diamond torch from Miller. This is the top of the line. That's all we deal with here at Weld Pro. I'm going to go over the torch parts with you. You have a cup. This is a gas diffusing cup. You have an insulator, which is this white part right here. This is the torch body. You have a cap. Now there's different size caps. You have long caps. You have medium-sized caps, all depending on what your welding needs are. Typically in the aerospace industry, my favorite setup is a short cap because I'm always clearance. I always have tight clearances that we have to get into, so I always keep a short cap on there that enables me to get in really tight places. So we're going to disassemble this, and we're going to get right to it. Now this cap right here, this is something that I would typically use for titanium or columbium or an aerospace type alloy, where cleanliness is very, very important, and oxidation. What you'll learn in welding is oxygen is not your friend. Oxygen causes hydrogen embrittlement. It causes cracks. It causes all sorts of problems. Now, the old school guys are going to tell you, when we're talking about the different kinds of collets that you're going to use. Us young guys, we like to use what's called a gas lens, and that's what this is. And what that is it's a collet, and it has a screen on the inside that helps a series of screens on the inside that helps to diffuse your shielding gas, and it gives you a prettier weld, a cleaner weld, an X-ray quality weld. Okay. Now we have our tungsten. This is a 2% thoriated tungsten. It's 3/32 in diameter. This is the typical size that you'll use. This is 3/32 in diameter. This is 1/16 in diameter. That's typically what you use in aerospace most of the time. A 3/32 or a 1/16 tungsten. Occasionally I'll go down to a 40,000 tungsten if I'm welding something very thin. Very thin, 4,000s, 5,000s, 12,000s thick. Typically, these are the kinds of cups that you will use. This is a number 7 Lind cup. And this is another type of gas lens. This is typically what you would see in a hobby shop, in a race car shop, in your typical job shop. This is good stuff. Okay, we're back and we're going to talk about the different torch parts that are available for you. And typically what I would be using in the aerospace industry would be what's called a gas lens. And this is a gas lens. This lens right here has a screen inside of it, has a series of screens that run down the length of the torch. They help to diffuse the gas. Now, you'll get a cleaner weld with this. You will get a prettier weld with this. I've done testing side by side with a standard torch bot, with a standard gas diffuser, which is what this is. And you'll see the holes along the side where the gas comes through the torch and flows out through the cup. And it works. The old school guys like these. But if you've done testing like I have and have welded stuff side by side, gas lens versus your standard, the gas lens always comes out on top. Gas lens can tend to be a little bit more bulky, but that's just the way it is. These are some other parts that we use. This is a short cap. This is a medium-sized cap. This is a long cap. Now, the long cap is something that I would use if I was bench welding, or if I was not space restricted. If I wasn't space restricted. Typically, I'll use the short cap. This is tungsten. This is a tungsten electrode. This is a 3/32 tungsten electrode. This is 2% thoriated. You're going to hear all different kinds of terms for tungsten. 2% thoriated, 2% serrated. The ones with the red on them, you'll have ones that have green paint on the end. People typically use those for aluminum. You can use the red. Red is a good all-around tungsten that you can use for everything. There's one with gray on the end that's called rare earth. Again, it's not necessary. It's not necessary for an X-ray quality weld. That's what I'm concerned with, putting down an X-ray quality weld every time. This is called an insulator. This goes in between the gas cup and the torch body. There are different kinds of insulators. This is typically a large insulator that you would use for a large gas welding cup like that. This is a number 12 from Lind. This is what I typically use for welding titanium or columbium or something, a material that gets hydrogen embrittlement easy from oxygen, where I have to use a lot of post-gas flow. This is the kind of cup that you would use typically in a job shop, a race car shop. This is what most people use. This is a good all-around cup, a Lind number 7. This is used with a gas lens. That's a gas lens again. Gas lens again has the screen and the multi-screens in there which help to diffuse the gas, which gives you a prettier, cleaner weld. Okay, now we have this torch here, so let's put this torch together. I'm going to set you guys up with what you would have in a typical shop, typical job shop, welding shop, race car shop, motorcycle shop, TIG welding shop. You're going to start with an insulator. You're going to take your insulator, put your insulator on the bottom. That helps seal gas, that helps seal electricity away from you. And something we didn't talk about was jewelry. You'll see that I don't have watches or rings, not even a wedding ring. So if you're looking for a reason not to wear a wedding ring, there you go. You don't want to have a wedding ring on when you're welding. That thing will turn, if you get grounded out, that will turn red hot and you will have a permanent wedding ring on your finger. Sorry, honey. Anyway, let's put this torch together. We're going to start with a 3/32 gas lens. We're going to put that in here. You're going to screw that in. And you want that to be tight. Don't put a pair of pliers on it, tear the threads up, just put it in there tight. Finger tight. Now, you're going to choose your cup. Typically, what you're going to be using is a number 7. Number 7 Lind. That's a good all-around universal cup. You're going to screw that on. You're trying to make a seal because you have to seal the gas. You have to seal the gas and the electricity, so you're going to tighten that up. Okay, now that's tight. Now you have a collet. We use a 3/32, so we're going to put our 3/32 collet in there, and we're going to put a cap on. And let's screw our cap on there. And we are ready to go. Now, the only thing we're missing is our tungsten, and we're going to go show you how to prep your tungsten. Okay, here is your 3/32 tungsten. Now we've cut a section off of another piece of tungsten, but it's the same thing. 3/32 tungsten. You're going to cut this into 3 pieces, or if you have a long cap on there, you can use a long one. I break it into about 3 pieces and sharpen it. Another thing you're going to need is a cordless drill. You're going to see these old timers sitting here they're going to have the tungsten in their hands, and they're going to be turning it like this, and they're going to be burning their fingers, which is, I've never understood why people do that. And if you really looked at a tungsten close up and you looked at the lands and the grooves of the tungsten under high magnification, you'll see inconsistencies. With using a cordless drill, everything comes out cleaner. It looks like it's machined after it's finished. And you're looking for an X-ray quality weld, so that's the way we do it here at Weld Pro. So what we're going to do is we're going to put the tungsten in the cordless drill, and we're going to prep our tungsten. Now, you're not looking to make this tungsten so sharp, because remember, most welds that failed X-ray fail because of tungsten inclusion, which means a piece of tungsten is inside that weld. You don't want that to happen. So you're going to make it sharp, but you're not going to make it so sharp to where you're going to burn a piece off, and it's going to fall into the weld. And the way you do that is after you finish prepping your tungsten, you put it in your torch and you fire the torch on a piece of material hotter than what you're going to be welding at. That's a common practice. So we're going to turn it on and get started. That is what you're looking for. You're looking for a nice point. A nice point. Not so sharp that it's going to break a piece off, but you do want it sharp. You definitely want to direct that weld current. Okay, while we're talking about welding, we need to talk about the welding machine also. That needs to be covered under the welding parts, torch parts, etc. This is a welding power source. This is a TIG welder, but this is something other than a regular welding power source. This is the latest from Miller. This is an inverter power supply. The first thing you see when you see this welding power supply is you notice the size. The size is very small. This is typically what I would use in a race car shop or in a confined space, or if I didn't have the room to move a big welder around. No longer are welders being made with really big magnet coils and all that kind of business. Now everything is real small, microprocessors, microchips, little capacitors. Welders have come a long way. This particular unit can run AC and DC, AC and DC. How about that? AC and an inverter power supply. This unit is used for TIG welding or stick welding. We use it for here at Weld Pro for TIG welding in shop. And here is your AC and DC power switch. Everything is push button. You see your amps right here on the screen. Your volts come up on that side. Right now we're running at 180 amps on DC. On the switch right here, this is a switch for TIG high frequency impulse or TIG lift arc. When we are concerned with doing X-ray quality weld, you do not want to be touching your tungsten to the workpiece. That is how you leave tungsten in a weld. You don't want to do that. In a race car, it's not going to matter. I do X-ray quality welding all the time. That's why I use a foot pedal. So you want that on TIG HF impulse. Yeah, there's a number of other switches. There's a pulsar on here. We'll get into that in some of the advanced later volumes of welding, but right now we're talking about basic TIG welding, so I'm not going to go into that with you and get you all confused. You have a post flow switch. Post flow is what covers your gas flow. That's covered in seconds. Push the button. That shows you right there how many seconds that purge stays on after your welding. That's critical in aluminum and stainless steel and titanium, because if you shut the gas off right after you're done welding, the material is going to blue. And in titanium, you're talking hydrogen embrittlement, which means cracks, and you don't want that. You have an AC wave shape. Some people like a square wave. You can adjust the AC wave balance right there. But again, we don't want to talk about that kind of confusing stuff. We just want to talk about your standard TIG welding. You have an amperage switch. This is the one that you are going to be moving all the time. We'll let our purge stop there. We got 6 more seconds. See, it's still on the purge cycle. That's going to stop. And back to normal. Now the other knob up here, right here, is your amperage adjustment. This is what controls your arc. Your foot pedal controls your fine adjustment on your arc, but your arc is controlled right here with your amperage adjustment. Today we are going to be welding 1/8 inch aluminum and 1/8 inch stainless steel, so we're going to be roughly at about 125 to 150 amps. So we're going to turn the machine up to 150 amps. 150 amps max. I'll tell you what, we'll go to 160, 170 just to be on the safe side. And you can always move that adjustment. Okay, and we're back here at Weld Pro's instructional video. Other torch parts that we did not talk about yet is you have these connections on the bottom of the welding machine. You have a ground. This gets grounded to your work piece or your welding bench, your welding table. You do need that to complete the circuit. If you don't have that to complete the circuit and you touch the table, you will find out what's going to happen. This is your foot pedal. This is, or your remote. If you look on your welding machine, you'll see typically where it'll say remote or lift arc. If you're doing where you have to touch the TIG torch to the work and then pull it off, that's a lift arc. You won't be using a foot pedal. I do not recommend that. Get yourself a foot pedal or a thumb switch on your torch. You definitely want that control. This is the foot pedal. Foot pedal screws in here to a 14-pin connector. This is the connector for your torch. Gas flows through here, through this hose, and through the torch. There's another kind of torch called a water-cooled torch. I use a water-cooled torch if I'm doing continuous welding for a long amount of time, typically bench welding, or if I'm going to be using a lot of amps. Today we're just going to be using at a max 170 to 150 amps, so we're using an air-cooled torch. Again, this is a state-of-the-art machine from Miller. This is the Miller Dynasty 200 DX inverter power supply. This thing weighs 40 pounds. It has 200 amps of welding capacity. You can make it weld more than that if you mix helium for welding aluminum. It's a very nice machine. It's top of the line. Okay, you're back with Weld Pro. This is Donovan. We just finished talking to you about welding torch setup, and now we're going to talk to you about some of the other equipment you're going to use as a welder. And one of the most important pieces of personal protective equipment that you are going to use is going to be your welding helmet. This is a typical welding helmet. This is what I use. This is a Huntsman 951P. It utilizes a larger welding lens for more greater visibility. A lot of the older guys like to use the smaller lenses. It's up to you, it's your preference. I typically get into a lot of areas where I'm visibility restricted, so I like to use that larger lens. The welding lenses come in various shades of darkness, 8 being the lightest and 12 being the darkest. You want to get in the habit of using the darkest lens you can possibly use. You want to protect your eyes. If you look at a lot of the older welders, you'll see that they have really, really bad eyes. And the reason why they have bad eyes is because they did not use a dark enough lens while they were welding. While we're talking about eyes, and you're going to be grinding as a welder, you want to get in the habit of using your safety glasses. You want to take time out for safety. Don't start grinding without using your safety glasses. If you lose an eye, you can't call that time back. The eye's gone. Use your safety glasses. Take time out for safety. You also use your gloves. This is a typical welding glove from Tillman, 1328. This is a leather glove. They make these gloves out of leather. They make them out of kid skin, deer skin. There's a variety of different companies that make them. This is pretty much an industry standard right here, Tillman. This is a very good glove. Guys, in the welding industry, you're going to come across production-minded people that are not necessarily concerned with your personal health and safety. Managers, supervisors, foremen, take the time out for safety. Protect yourself. Use your PPE. Your family's expecting you to come home in one piece. And as promised, I'm not going to bore you with a bunch of classroom book work, etc. We are going to start welding. So today, I told you we're going to weld stainless steel and we're going to weld aluminum. Here in front of me, we have two plates, 6-inch plates, 6-inch by 4-inch stainless steel. This is 316 material. We're going to be welding this with 316L. This is going to be our filler wire right here. This is aluminum, and the aluminum is 6061 T6. I chose 6061 T6 because typically in the aerospace industry, that is what you run into most of the time, is that 6061 aluminum. They like to use that in a lot of injectors, a lot of rocket engine parts, satellite parts. Any place where aluminum is used, you typically will find 6061 T6. There's different kinds of aluminum. There's 1100 series, we weld 5000 series aluminum. All of them require different techniques, but 6061 is a typical aerospace alloy that is used in aerospace, semiconductor. It's a universal aluminum that's widely used in the industry. The stainless steel that we chose is 316. Typically what you'll see is 308, 308L, 316, 316L. Be careful if you guys come across 303, 304, stuff like that. You need a little bit more instruction with that because it's very crack prone. Yeah, so that's what we're going to be welding today, and I'm going to show you how to do it. Okay guys, we're getting ready to weld stainless steel, and I'm going to give you my reference settings for welding stainless steel. First, we're going to start with our shielding gas. Our shielding gas is argon, straight argon, and the flow rate that I use with stainless steel and titanium is 30 CFM at the top of the ball, and I'll show you that right now. We'll hit the pedal and you'll see that steel ball in there is set at 30 CFM, and that will allow you to have the pretty colors in the stainless, the reds and the blues and the straws, and that's what you want your flow set at, 30 CFM. And of course we're going to be running DC polarity, so we're going to go over to our machine and take a look at our polarity switch, find your polarity switch. This is a push button on most machines, it's a big knob, but find it and set it to DC. And you are going to be setting your amperage at 120, and you'll see that in 1 second as soon as that flow rate stops, and it's set at 120. And we're not going to use the whole 120. I might be using 85 to 90, but you want to have it set at about 100 to 120 because different positions will require different amperages. Welding a flat butt joint is not the same as welding a vertical up or a T-joint. But 120 will put you in the ballpark. You're going to control the amperage with your foot and the remote that you have. Yeah, the remote is your foot pedal. That is how you control that amperage. Okay, back with Weld Pro. This is Donovan. We are getting ready to weld stainless steel. We're going to weld stainless steel in a butt formation. This is 316 stainless steel, roughly 1/8 of an inch thick. We're going to weld that in a butt formation, putting those two pieces together. But before we weld that in the butt formation, we've got to do a weld prep on it. What we're going to do is we're going to put a 45-degree bevel on the weld surface of each side of that plate. So we're going to put the stainless steel in the vise, and we are going to prep the material. Okay, we've got our stainless steel secure in the vise, and we're getting ready to prep the material. First thing you're going to do is grab a hold of your safety glasses, put those on, and we're going to cut a 45-degree bevel on this edge and on the other edge of the plate that we're going to weld the butt joint on. So we're going to prep that plate right now.
we've put a 45-degree bevel on this plate, and we'll get a close-up shot. That is what your bevel should look like. You should have a 45-degree bevel on it. Okay, we've got our other piece for the butt joint affixed in the vise, and we are ready to prep that material also. And again, your safety glasses are on your face. And we're back with Weld Pro. This is Donovan. We have just finished prepping our 316 stainless weld certification or test plate. We have cut a 45-degree angle on each edge of the two plates that we're going to butt together and weld it. And we're going to put 3 tacks on that plate to hold it. And what we're going to do is the mismatch has to be controlled. And by mismatch, I mean putting those 2 plates down, making sure that they're both on the same plane. Making sure that you don't have any mismatch. One plate sticking up higher than the other. That is a criteria that inspectors look at when they are certifying you. You want to make sure that mismatch is correct. You want to make sure that you have your plate adequately tacked, because you don't want to tack to pop while you're in the middle of the weld. So again, we've got a 45-degree angle cut on that plate, and we're going to butt that plate together. And before you do your weld, what you need to do is wipe your plates with acetone. Make sure this is off the table before you start welding. Wipe your plates with a lint-free towel if you have that available. If not, just make sure that they're clean with acetone. And we are getting ready to start welding the plates. We are finished prepping our material. We have cut a 45-degree bevel on each one of these stainless steel 316 plates. And what we're going to do is we're going to tack these together. We're going to put the 2 plates together. As such, you want to be mindful of your mismatch in that plane and your mismatch in this plane. You want to make sure that there are no gaps in the plate, and you want to make sure that they are on the same plane. So we're going to put the 2 plates down on a flat surface on your welding table, and we're going to clamp them. And after they're clamped, we're going to put 3 to 4 tacks to hold that plate. Always being mindful of that mismatch. That is what will fail X-ray. Now you go to your approved filler material, which is 316L. You know that's 316L because you've looked on your box and you've verified that you have 316L as your filler material. You always want to make sure that that's right. Make sure you have your right filler material. You don't want to fail an X-ray for something silly. Now we're going to proceed to tack this plate. You always want to get your gas flow flowing first before you tack, because if you tack the plate before having your gas flowing, you'll get porosity. So I'm going to hit the gas pedal, hit the foot pedal. Gas is flowing, and for reference purposes, I have the weld machine set at roughly 100 amps. I'm not going to use the whole thing. I'm using about 75 to 80 of that, and the gas is flowing at 30 CFM. Typically, you want to use 10 to 20 CFM when you're TIG welding. Stainless steel, I like to use 30 because it gives you pretty color. It helps cool the plate also. So again, we're going to get the gas flowing, and we're going to tack the plate. Beautiful. 1 tack. 2 tacks. Now what I'm going to do, I've got the torch held on there because remember we talked about oxygen not being your friend. You don't want to oxidize the weld metal while it's still hot. So you keep the torch on the material that you just welded. I'm going to flip the plate around and we're going to reclamp it. In a more friendly position. And we're going to proceed to tack again. Again, get the gas flowing. one tack. I'm going to move the clamp, and we're going to put the last tack on the plate. Again, keeping the gas on the welded material. You don't want that to oxidize. Okay, now what we're going to talk about is torch angle. I do not have an exact angle for you. Everybody's different, but this is basically what it looks like. This is the angle your torch should be at when you're making your weld pass. You should be at that angle. Your tungsten should be about 50 thousandths off the material. 50 to 60 thousandths off the material as you weld down that plate, and you're going to be welding down the center of that joint, and you're going to make a solid root pass. And what you're looking for is you're looking for liquid molten metal. You're not looking for a keyhole or any of that business. You're looking for liquid molten metal. And once you see that puddle form, you're going to pull that puddle forward. You're going to stop. You're going to add your rod, and you're going to back up. And you're going to do the same thing. Pull it forward, stop, add your rod, back up. Pull it forward, stop, add your rod, back up. That's how you form weld beads. Okay guys, we have a butt joint that was previously welded here, and we are setting up the machine, getting ready to weld a butt joint that has a weld prep, 245-degree angles cut on each side of the material. And the machine's at about 150 amps here, and we're laying down a weld bead right next to a previous bead, making sure that our machine settings are correct and making sure our gas flow is correct. And what you're seeing now is the weld. You're seeing liquid right there underneath the tungsten in a brighter lit area. You're looking for molten metal right there, and you want to make sure that your edges are tied in on the weld, and that's what we're looking for. You want to make sure that you got a 3/16 stainless steel wire for our filler material, because that's what we're welding right here. This is in the middle of the plate where I had to stop for a second, and you'll see where I let off the pedal and began welding again. So all I did was just let up on the pedal a little bit and to get my bearings right with my hands and come back into it. And we continue to add rod, and we're getting our focus back. And we continue to weld and add rod. You'll see the molten material, and you're pulling the torch forward as you're adding the rod. You're keeping your rod underneath your shielding envelope. That's very important. Now we're coming to the end of the plate, and you're going to see me tail out very slowly and add a little bit of extra rod. And what that's for is so to prevent cracking. Now we are on our butt joint in stainless steel 3/16. You can see as I am filling up the weld prep and seeing the shiniest part up underneath that tungsten is where the molten metal is, and you can see I have the 3/16 filler material right underneath that cup. It never leaves underneath that cup. That's very important. If you pull it out of that cup, it's going to oxidize, and you're going to put oxidized weld material back in there, and there's a chance for porosity. Again, with an X-ray quality weld, you want to make sure that you keep that filler material underneath that shielding arc. You can see the angle of the torch by looking at how straight the tungsten is. That gives you a baseline for your welding angle, and it's about 50 thousandths off that material. And again, you're seeing molten metal. I'm not pulling that torch forward until I see molten metal moving forward, and then I'm adding rod and slowly backing up. But the metal, you put the rod right there in that torch, it'll take exactly what it wants. You don't have to force anything in there. You just want to put enough rod in there so you can see a crown form. After you see that crown form, move on. You don't want to overheat the material. And you can see it's kind of rhythmic. Once you get started and the plate gets hot, yeah, everything flows together really nicely. And again, we're coming up to the end, and we will tail out very slowly. Add a little bit extra material right there. Take your time and let off slowly so you don't get a crater or a crack. Okay, we just finished welding our stainless steel butt joint out of 3/16 stainless steel. This is what a finished weld should look like. This was the start of the weld down here. We welded this in the flat position This was the start of the weld where you're going to have greater amperage to get that to fuse. And then stainless steel, as it gets hotter, it does not require as much amperage. But you're looking for nice colors, the reds, the blues, the straws, no blacks. Yeah, that's what you're looking for. Yeah, each bead interlocked behind the other. The toe, you don't want any undercut on the toe of the weld, which is out there on the edges. You want the crown of the weld to stick up roughly 10% of the material thickness that you're welding. Of course, this was 1/8 inch material. Yeah, so you want that to be sticking up about an 1/8 inch higher than the parent material. This is parent material. This is the weld material. So again, that's what you're looking for. And this was done in the flat position. We have concluded the butt joint welding. Now what we're going to do is weld a T-joint. The reason why they call this a T-joint is because it looks like a T. This is a welded T-joint that I've already welded. And what we're going to do is we're going to set our material up. This is what we're going to use for the bottom piece. This is what we're going to use for our T, for our top piece. You're going to clean these plates with acetone, verify that they are clean, and we're going to put 4 tacks on the plate. 1 on each end and 2 in the middle. I'm going to set this plate down in the middle, verifying that that is the middle. And I am going to hit my gas pedal to get the gas flowing on the torch. And I'm going to put a fusion tack on this end. Again, making sure that I keep the gas on and keep the torch over the material after it has been tack welded so it does not oxidize. You should see shiny stainless steel. Now I'm going to flip it, get the gas flowing again, and we're going to do the same thing on the other side. And that looks great. Now what we're going to do is we are going to put a tack on the back side of the plate. 2 tacks rather. Get our gas flowing, that's very important. And you can put a nice fillet tack. A nice fillet tack right there. You're going to keep your gas flowing on the plate so it does not oxidize. I cannot stress that enough. Going to move down here and you're going to do that one more time. Get your gas flowing. And a nice fillet tack is what we have. Okay, here we are with a T-joint in 316 stainless steel, and you'll see that we've got the puddle is molten, the torch is lit, and we're welding right along. I'm welding kind of fast because you can see the puddle is molten, and we're adding rod, and as long as that puddle is molten, you want to keep moving. You don't want to force, and again, making sure that rod is up underneath that shielding gas. That is very critical, especially with stainless steel and aluminum. This is stainless. You can see the reflection off of that material, off of that 316, but you can see that liquid metal. That's what you're looking for. You're keeping that puddle molten. You don't want to pull it and see any kind of a gap or a keyhole, which a lot of guys talk about welding and filling keyholes. All you're looking for is molten material, and you're adding your filler rod, and the puddle will take exactly what it wants. You just want to put enough in there just to make a crown, and that's it. If you try to force too much, the rod's going to stick. If you don't force enough, it's going to be very concave and it's going to crack. And again, with every TIG weld, as you come to the end, you want to tail out, take your time, let off the pedal easy, and add a little bit of extra filler material so you do not have a crater or a crack. Okay, we just finished our T-joint in 316 stainless steel. And this is what you should look for. This is what a finished weld looks like. It has pretty colors, the reds and the blues and straws. You don't want any black. You're looking for each bead to be locked in behind the other one. You want everything to be clean. You want the toe of the weld, the edges of the welds no undercut, and the appearance is nice. The appearance is a pretty weld. That's what you're looking for. Okay, back with Weld Pro. We have concluded our segment on welding stainless steel, TIG welding stainless steel. Hopefully you guys picked it up. We're going to move on to aluminum. This is a 6-inch aluminum plate, 6-inch by 1/8 inch T6 6061 alloy aluminum. Now, aluminum, like any other material, is different than any other material, rather, because aluminum builds an oxide very fast, and we have been talking about how oxygen is not your friend in welding, especially with aluminum. As soon as aluminum is machined, it immediately starts to build an oxide. You'll see a cloudy, cloudy film on the aluminum. So what you have to do is you have to brush that off, and make sure you do it every time, because that is what makes aluminum weld good. We're using a stainless steel, we call it a stainless steel toothbrush in the welding industry, and it's just for that reason, removing oxide. And I'm going to show you how to do that. Take the plate, and you're going to brush the joint that you're going to weld. You're going to have some people tell you to brush in only one direction, some people tell you to brush in only 2 directions, but look at the aluminum, and you're not looking for it to polish the surface. You're looking for it to remove the oxide. You want to see a clean surface. You're going to do this on the front and the back of the plate. This is how you weld aluminum. These are the little tricks that they're not going to show you in a textbook, but you're learning this from a person who welds in the aerospace industry every day and has welds that consecutively go through penetrant inspection, x-ray inspection on a regular basis, 10, 15 a week. Now we're going to brush the other side, and you're going to hear people talk about, oh, they can weld soda cans together, they can do this, they can do that. Well, you ask them if they weld and have their welds go through x-ray. That's what matters. All the rest of that stuff is baloney and wives' tales. So we're going to continue cleaning that plate. Just like that. We're going to clean our other plate, which we got a head start on. Brush the joint. And brush the other side. Again, you want to get that oxide off of there. That oxide melts at 4,000 plus degrees, where a regular standard aluminum without the oxide melts at about 1300 to 1700 degrees, depending on what alloy and what hardness. T6 goes at about 1300 degrees. You're talking about like 17.7 Crest, or one of, excuse me, not 17.7, but 5000 series. That melts at a higher temperature. Okay, you're back with Weld Pro. This is Donovan. We are going over the TIG welding of aluminum, AC TIG welding of aluminum. And while welding aluminum, we mix our gases, our shielding gas. We have straight argon and straight helium. This is not a mixed gas. We mix this gas ourselves so we can control the penetration. There are mixed gases out there. There's nothing wrong with them. This is just the way we do it. We're looking for x-ray quality welds every time. So I'm going to tell you how we do this. We have a Y valve. This is a Y valve. These are two anti-backflow valves. You can see the arrows on the valves. You can buy those from your local welding store. And we have them going to regulators, and that's how we do it. And then that feeds the machine. Okay, so what we're going to do is we're going to set our flow meter on our argon bottle at 20 at the top of the ball, and we're going to set our flow meter on our helium bottle between 10 and 5. And you adjust that helium according to the thickness of the metal. The thicker the metal, the more helium you want. The thinner the metal, then you want to back off a little bit. But helium makes aluminum do makes aluminum weld better. Remember that. It makes a cleaner weld. It makes it go through x-ray easier, less holes, less gas holes, less porosity, less indications, and that is what you're looking for. So we're going to set this gas at 20 at the top of the ball in our argon, which is 20 right there. Now we're going to cruise over here to our helium, and we're going to set that between 5 and 10, and we're set. Okay, now let's talk about the setting of the machine for aluminum. And first we're going to be running AC, so we're going to set our polarity switch at AC. And amperage requirements for 1/8 inch aluminum is roughly about 130 amps, 120, 130 amps. And again, you're probably not going to use the whole thing. You'll probably end up only using, you'll be using about 120 on the startup. And then as you get into the weld, it'll probably drop back to about 90 or so. Again, you're going to regulate that with your foot control. Now, that is the settings for AC. Now, the settings for DC. All you're going to do is push your polarity switch or turn your knob to DC, and you're going to begin welding. Now, the difference between welding AC aluminum and DC aluminum is AC, you are going to preheat the part. It's going to take a minute for that puddle to form. It's going to get warm, and then it's going to get fluid, and then you're going to run. That's AC. But now with DC, as soon as you light that arc, it is ready to weld. So you start feeding rod. That is the difference between AC and DC. After that, all the movements are basically the same. Okay, we're getting ready to weld this aluminum butt joint. And what I'm going to do is I'm going to give you a dry run to show you from beginning to end what is going to happen in the beginning of the weld, what's going to happen during the weld, and towards the end of the weld. During the very beginning of the weld, the very first thing you're going to do is you're going to hit your foot pedal and get your gas flowing. Okay, now the plate has already been tacked together. Again, this is a dry run, so we've got our gas flowing and we're going to start the weld. And our machine is set at, say, 120 amps already, but you're not going to floorboard your pedal, because if you do that, you're going to blow stand a chance of blowing a piece of tungsten off the tip of the electrode into your welding. You don't want to do that. You want to bring in the amperage slowly, just barely light the arc, get it warmed up until you see the puddle become molten. Once the puddle becomes molten, then you want to start your weld. You want to add a little bit of rod, you want to get it molten, add a little bit of rod, and you want to bring that puddle forward, and then you want to back it up, and you want to add a little bit more rod, and you want to increase your amperage now, and then you want to keeping the puddle molten the whole time is the key. The puddle is molten. You want to add your rod. Bring the puddle forward, back it up, add your rod. Bring it forward, back it up, add your rod. Bring it forward, back it up, add your rod. The whole time while you're welding, you want to keep this rod underneath the shielding gas envelope. You don't want your rod all the way out here because it's going to be getting oxidized. You do not want oxygen on the end of that rod. That'll cause you to fail. You'll keep your filler metal underneath that shielding envelope while you're welding. Forward, back up, add your rod. 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 And so on till you get to the end. Now, as you're welding the aluminum, the plate's going to be getting hotter and hotter and hotter, and your amperage, you're going to have to back off on your foot pedal to keep your weld width uniform throughout the whole length of the plate. And then as you get towards the end of the weld, the plate's really going to be getting hot, and you're going to be backing off more on the amperage. And then as you get to the very end of that weld, you want to add a little bit of extra rod in there, and then you want to do what we call tail out, which is let off the remote or the foot pedal very, very slowly, and move your tungsten in a circular position so you don't leave a crater. And that is basically it. And that is true with stainless steel, aluminum, mild steel, titanium, all of the welds. You want to start slow, bring up the heat in the beginning, and just the opposite at the end. You want to let off slowly and move your tungsten around in a circular position with a little bit of extra filler material so you do not have a crater. Because if you have a crater, you have a crack. And here we have a butt joint welded, an aluminum butt joint, and you can see we're at the beginning of the weld, and remember I said aluminum you have to preheat while it's on AC, so we're allowing it to warm up and we're adding our rod. again, you want to keeping your rod underneath the shielding gaps and adding it to the puddle, and it'll take what it wants. It'll take exactly the exact amount that it wants. All you want to do is have enough in there to where you create a crown. And here we're readjusting, and you saw me let off right there and get readjusted and got my bearings with my hands. And we're continuing to weld the butt joint. You're seeing the molten metal and pulling it forward, adding our rod, pulling it forward, adding our rod, keeping it molten, adding our rod, forming beads. One interlocking bead right behind the other. You can see that bead form. That's what we're looking for. That is a successful. That will be a successful X-ray quality weld right here with this butt joint. You don't see any porosity popping. It's not overheated. We're moving slow. We're not going fast. And we are adding our rod. Adding our rod, and you can see it takes exactly what it wants. I'm about 50 thousandths from the workpiece. The weld has good width. The edges are tied in. The toe is tied in. We're not dipping our tungsten. We're not dragging our tungsten. Hand is steady. And that is what you are looking for. That will give you success right there. And we're going to come back in focus here in a second. And again, this is a lot clearer than the stainless steel. You can see the molten puddle better, and aluminum is a little bit slower welding at AC. And we're coming up to the end of the plate. And again, we're going to be, I'm letting off the pedal a little bit here because I'm coming to the end of the plate. And it's not requiring as much amperage just because the plate is already hot. And as we get to the end of the plate, I'm adding a little bit extra filler material to kind of cool that puddle off and prepare for that end and prepare for that tail out. And as we tail out there. Okay, we just finished welding our aluminum in the DC polarity. This is 6061 T6 aluminum. And this is what a finished weld should look like. Each weld bead locked behind the other. And aluminum being welded DC is not like welding at AC. You just light the torch and start running. AC, you have to sit there and let the part heat up for a while, but DC gives you a driving force in the material, and the heat is there immediately. As soon as you light the torch, it's there and it's ready to go. And that is what a finished weld should look like. And you want that crown of that weld to stick up 10% proud of the parent material. Again, the parent material is the sides of the plates, and the weld is in the center of the plate. Okay, now we're set up to weld our T-joint in 6061 aluminum, and I'm going to dry run this to show you guys what is going to be happening at the beginning of the weld, during the weld, and at the end of the weld. And the very beginning of the weld, what we're going to do is we're going to light the arc and with minimal amperage, and we're going to bring the amperage up very slow. Again, you don't want to floorboard that pedal because you'll blow a piece of that tungsten off into your weld, which will cause you to fail. So what's going to happen is you're going to light the arc. Then after you light the arc, you're going to bring the amperage up, and then you're going to add your rod. And then after you add your rod, you're going to bring that puddle, that molten puddle, forward, and then you're going to back it up, and you're going to add more rod, forward, back up, 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 add more rod, etc. And the amperage requirements as you get into this weld are going to be less because the plate is going to be heating up. The material is going to be heating up, and it's not going to require as much amperage. And then when you get down here towards the end, it's going to require even less amperage. And remember, when you finish the aluminum weld, you want to add a little bit of extra material there and move your tungsten around and bring that amperage down slow that you're regulating with your foot control until the arc goes out. And what that does is that prevents you from having a crater, and especially in aluminum, which is crack sensitive, you don't want to have a crater. So let's go back to the beginning and start the weld. Okay, this is a 6061 aluminum 1/8 inch T-joint, and we were getting the plate warm, getting the puddle warm, and now we're beginning to add our rods. We're taking our time. Saw that big chunk of go in there because it wasn't quite ready. Now it's nice and molten, it's ready. You see that liquid molten metal, and you're pulling it forward, and keeping that shielding, keeping that rod in that shielding gas is critical. And we're adding our rod, we're slowing down, adding rod, slowing down, back up, slow down, back up, add rod. It happens very fast, but you can see the rhythmic movement that you need to do that. Keeping everything molten, making sure the edges are tied in well. If you're carrying too much heat, too much amperage, you're going to undercut at the top of the weld. So back off on your foot pedal, or either turn your amperage down, whatever suits you best. But you want that crown to be uniform top to bottom. And you want it to be convex, not concave. And at the end of the weld here, we're going to slow down and tail out. Okay, we just finished welding our 6061 T6 aluminum and a T-joint formation. And you can see here, this was welded AC, not DC. This was welded AC. And what we're looking for is each bead to be interlocked behind the other one with no visible porosity in the weld and the top of the weld. You know that's a clean weld. You can look at the toe of the weld and see that there's no undercut. The edges look nice. Each bead is locked behind the other bead. That is what you're looking for. And with AC, at the start of the weld, which is here, it requires more amperage to get that started and get it all warmed up, and once it's warm, it's ready to flow. And then we started the weld, and as you weld, it requires less amperage because the aluminum holds heat incredibly well. So again, the start of the weld requires more amperage. Then as you get to the middle and towards the end, where it requires less amperage. And you're looking for each bead to be interlocked behind the other one. That's what a proper weld should look like. Well, that about sums it up for our aluminum portion of the instructional welding DVD here at WeldPro. There is something I want to talk to you guys about before we conclude, and that is tungsten inclusion, or dipping your tungsten in the weld metal. You want to take the time to get a clean carbide burr and use no coolants, WD-40, anything that can impregnate that metal and cause a failure as far as certification goes. Take the time to get a clean carbide burr and carve out that inclusion, or as the people in X-ray call it, a MDI, a more dense inclusion, tungsten being more dense, so it shows up bright white on an X-ray, so you will not hide it, they will see it. So make sure you get it out of there and replace that with clean weld metal. I hope the information that you guys have seen is informative and will help you in your welding career. We have covered tungsten preparation, we've covered shielding gases, we've covered machine setup for stainless steel and for aluminum, in the T-joint formation and in the butt joint formation. Remember guys, always wear your personal protective equipment, your PPE. Safety is the most important thing. Safety over schedule. Always remember that. I hope the information again that you guys have seen is informative and helps you in your welding career. And here at WeldPro, we wish you the best in your welding career.